Okay, moving on to the second page here of the practice exam, practice version for exam 3. We've got another question here kind of relating to electron configurations, right? Not quite exactly quantum numbers this time, but the following electron configurations represent excited states. So an excited state would mean an electron has been moved up into a higher energy level than it would normally occupy in the lowest possible energy configuration, which would be called the ground state. We want to identify the element that is being described and write the ground state electron configuration. So I think the best way to approach this problem is just to figure out how many electrons are present. If these are neutral elements, if we know how many electrons there are, then we can find in the periodic table what element that would be. So looking at the first one, 2, 4, 6, 7 total electrons. Right? And if I just fill 7 electrons into the known order, that would be 1s2, 2s2, 2p3. Right? In fact, looking back here, we can see 1 electron was promoted from the 3p up into the 4p here in this excited state. That configuration, right, we could find that in the periodic table, right? 3 into the 2p sublevel, but also 7 electrons would mean the neutral atom would have 7 protons. This would be nitrogen. Right. And the other two maybe are a little more complicated because we've got the noble gas abbreviations in here. So this one is argon, right, plus 1 plus 10, 11, 16, plus 17 electrons. So starting from argon, if we fill in 17 electrons, let me grab the periodic table. And argon is over here, it's 18. So after argon, we would fill the 3s, right? And then we can use the periodic table to go from there. That would be 3s2. Let's see. Actually, nope, I'm counting wrong. It's 4s. 4s2. Then the 3d, which could hold 10, right? And then we would hit the 4p, which could hold the remaining 5 electrons. If we already did 12 there, that would be 5. So what happened in this case, one of the electrons that should have been in the 4s got bumped up to the 5s, right? And here in what would be the ground state, it would have fallen back to the 4s. Now, if we followed that across the periodic table, right, 5 across the 4p, that gets us to bromine here. Now, we could count electrons here as well. There'd be 18 with argon. We added another 17. That's 35. Right? But that's a little further afield from the first problem where we've got to account for how many electrons are in that inert gas. Krypton is a similar issue here. Krypton is 36. That means the next element would be rubidium, right? And that would be 1, 2, 3, 4, 5. That would be the 5s. So after krypton, right, we'd fill the 5s. Now, in the configuration we're given, 2 plus 6 plus 1 is 9. We've got 9 electrons past krypton. So after the 5s, what would come next is the 4d. And we can just put the 7 electrons here in the 4d. Right, so in the excited state, 1 electron was bumped up from the 4d to the 5p. It falls back down into the 4d. We would have that configuration. So 7 into the 4d, 1, 2, 3, 4, 5, 6, 7 would be rhodium, or RH. Okay. All right, number 5, continuing with some discussion of electron configurations. What is the complete electron configuration, no abbreviations, of the atom that would reside below Rentgenium, element 111, in the periodic table? So here's our periodic table, right? And here's Rentgenium, element 111. Now the key here will be to figure out what the end of the electron configuration for Rentgenium would be. So where we are here is a D block, 3D, 4D, 5D, 6D. So we're in the 6D, and that would be 1, 2, 3, 4, 5, 6, 7, 8, 9 into the 6D. So Rentgenium ends with 6D9, right? So whatever would come below it, if we continue the periodic table, would mean this mystery element would have to end 7D9 to occupy that same spot on the periodic table. So what we need to do here is build up an electron configuration up to 7D9. Now, the way I would recommend doing this, right, we're going to have to go past what is shown on the periodic table. So we can do this with what we know about quantum numbers. So there's this little sort of half pyramid you can build where you show all of the possible sublevels, and then the ordering is kind of diagonals through them based on n plus L values. So you might want to kind of work that out. That'll help you see where to fill all of your electrons. So 1s, 2s, 2p, the 3s, third would have a 3p and a 3d. Fourth would have s, p, d, and f. The fifth would have s, p, d, f, and g. The sixth would have s, p, d, f, g, and h. Right? And then we're not going to need all of these, so I don't have to fill the 7 all the way out. Let's go out to f. And we can always add a little more if we need to. So let's see if that gets us there. So I filled the little chart out to the 9p. Now, the order is going to be based on n plus L values, so it cuts through in diagonals like so, right? And whichever one you hit is the one you fill next, right? So if we follow that, we would get, right? And it's going to mimic the periodic table, at least until we get to the end of the periodic table. So you could get up to 118 just using your periodic table. 1s2, 2s2, 2p6, 3s2, 3p6, right? That would be there. 4s2, right? That's as far as I did the diagonals. Then would come 3d, that'll be 10, 4p, 6, 5s, 2, 4d, 10, 5p, 6, 6s, 2. Then I would hit the 4f, right? Again, you can find that on your periodic table, might help as well. 5d, 6p, 7s. All right, 5f. That'll be 14 in an F sublevel. 6d, right? So there's where we would pass Roentgenium. 7p, 6, right? Now, that's a good place to maybe stop for a second. That's where the periodic table ended, right? At element 118, 7p6. So we're now going past the periodic table. That's where this is really going to help. The next set of orbitals we should encounter is the 8s sublevel, right? Now, after that, here's the one that people will sometimes forget about, the 5G. So 8s will be 2, 5G, right? Now, watch the pattern here. 2, 6, 10, 14. We're adding 2 more orbitals every time we have a higher sublevel. So we'll be able to put 18 electrons into the 5G because it'll contain 9 orbitals. Then we would hit the 6F. We'll have to fill that all the way up to get to the one we're looking for. Remember, we're trying to get to 7D. So 7D9 would be the final sublevel that is partially filled in this case. Okay. Now in this case, we could count here as well. We were at 118 when we finished the 7p6. So after the 8s, we'd be at 120. After the 5g, we'd be at 138. After the 6f, we'd be at 152. So this would be element 161, right? If that was what was asked in the question. Certainly that's another way you could kind of phrase this question. All right, that's the electron configuration. Going on to part B. If the element above were to form a +4 ion, what would its electron configuration be? Okay, now a +4 ion, that would mean we're removing 4 electrons. So we got to take away 4 electrons. Now, nobody knows, of course, what would happen with this element because it, of course, doesn't exist. We don't see it represented yet on the periodic table. In fact, it's way away from any of the ones we see. But I think the best way to answer this would be to take them from the S first, because we know that's what happens with other transition metals is when you start to make a cation, those S electrons are the first ones removed. So I couldn't say you were wrong if you took them all from the 7D. That would be, as long as your numbers worked out in your configuration, that would be fine. But I'm going to take 2 from the S, and then I'm going to take 2 from whatever the next highest in the electron configuration is, which is the D. And I'm also going to use the abbreviation here. It doesn't say I have to do no abbreviations here, so I'm going to use the abbreviation. And I'm going to use oganesson for my abbreviation. That's 118. Now, the periodic table we use hasn't updated yet with Oganesson, so if you use UUO, right, which is basically 118 placeholder name, that's fine as well. And I took them out of the 8S, so that's not there, but it would be 5G18, 6F14, 7D, and I took 2 from the 7D, so that would be 7, right? And it would be the same here if you use element 118 for your abbreviation, right? What comes after it would be exactly the same. Now, part C, right, kind of relates this back to quantum numbers. What would be the quantum numbers of the electrons lost to make the cation? So we would have to think about the orbitals we took those electrons from. So if I start with the 8s, I took 2 electrons out of there, and that means the electrons had to have paired spins, right? This would help. Now, if it was the 8s sublevel, that means n is equal to 8 and L is equal to 0, right? And it would be so for both of those electrons. M sub L can only have one value if L equals 0, so M sub L is 0 for both of these electrons as well. But since they're in the same orbital, their spins would have to be different. One would be plus 1/2, and the other would be minus 1/2, right, for those 2 in the 8s. Now, we also took 2 out of the 7D. The 7D, that's a degenerate set of 5 orbitals. So the 9 electrons that went in there would have entered 1, 2, 3, 4, 5, right? All spin up because of Hund's rule. 6, 7, right? And then the ones we're going to end up removing are that one, 8, and 9. The last 2 in will be the first 2 that we take out. Now, those are both in the 7th energy level, so this would be n equals 7. They're in a D sublevel, which would be L is equal to 2. Right? Remember, S is 0, P is 1, D is 2. Now, they're in different orbitals, right? So there isn't a specific match between the value of M sub L and which of these orbitals there is, because M sub L is really just telling us how many, right? But part of the information here would be representing that these reside in separate orbitals. So you can't just list out all the values for M sub L. That doesn't give the information that these electrons are in different orbitals. The way I usually do it is from negative to positive, right? But again, that's not a convention. You could number them any way you want. What I would be looking for here is that you're giving me 2 different values. That shows me you know these electrons lived in different orbitals before they were removed from the atom in question. Because these were both the second electron that went in, they are both spin down, or M sub S equals minus 1/2, right? And that would depend on how you filled that orbital in the first place, how you would decide what the spin of that electron was. Okay, we'll take a break there at the end of that page. We'll come back with the 3rd page of the practice exam.